Welcome back to Chapter 17, which is our aqueous ionic equilibrium. I'm Dr. Rhonda Kofelt. In this section, we're going to look at some of these titration curves and we're going to compare them. And we mentioned this briefly in one of the previous sections about how if you have a strong acid, strong base, your equivalence point is going to be right at 7.0. And remember, equivalence is where you have the concentration of the acid equal to the concentration of the hydroxide. And so this is a very typical curve. You know you're starting with a strong acid because it's below 2. You're going with a strong base because it's above 12 when you get done. And then you have a pretty straight area where halfway between that is going to be your equivalence point. And as I said, it's going to be 7.0 with a strong acid and a strong base. If you have a weak base, or let me do this one first. If you have a weak acid and a strong base, notice that your weak acid is going to start a little bit higher usually than close to 0. The angle is going to be a little less pronounced, okay, as opposed to this one, which is a little flatter. Your straight area is a little smaller usually, so you don't have that real long one. And then you're going to end up with in your strong base area of greater than 12. So notice that the equivalence point that is halfway up this straight area is around 8.1 in this case, and that makes sense to us because we have a weak acid and a strong base. So whichever one is stronger, the pH is going to be on that end of the pH range. The weak base and strong acid is going to start with a base that's going to have a high pH. Notice that it's going to have, again, it's almost exactly the same curve, except it is going from base to acid. And your equivalence point, since you have the strong acid this time, is going to be below 7. And so it's going to be, in this case, about 5.3. So when you're looking at titration curves, you can actually tell what you're titrating, even if it's not labeled, by looking at the shape of the curve and the different areas. And so just like we saw that first one where we were looking at, all acid, buffer, and then all base, you're going to see that same type of pattern in these. So if the Ka mostly we've looked at monoprotic acids. You can have diprotic or polyprotic acids. When you do that, they're actually going to have 2 equivalence points, and that it coincides with losing the first H plus and then losing the second. Okay, and so because you've got 2 hydrogens, so in H2SO3, you're first going to go to HSO3 minus, and then you're going to lose, so you lose one of those, and then you lose that second one, and you're just going to go to SO3 2 minus. And so you've got 2 areas of equivalency, and so you're going to see a pattern something like this. When we're not doing a lot of calculations with polyprotic and even diprotic, mostly monoprotic in this level. All right, so monitoring pHs during a titration, we've seen using an indicator solution. You can also use what's called a pH electrode, and a pH electrode is a gas sensing electrode, and it senses the passage of those H pluses across usually a glass bulb. And so it changes the voltage across a selective membrane that these are passing across, and so that signals a change in pH, and it allows you to do a real-time titration curve rather than going after the fact and putting it on graph paper. So if we just need to know, though, how many milliliters it takes to reach the end point. Usually we just use a color indicator because it's a lot easier to set up. You just put a few drops in your liquid and then just go ahead. When it changes color at the end point, you're assuming that the equivalence point has been reached, and so you want to make sure that you have something that's going to change color right when you're expecting it to. So for most titrations, you're going to see a really large change in pH close to the equivalence point, okay, that coincides with that almost perpendicular area of the curve. And so since that's the case, you want to choose an indicator that's going to change color around that pH area. Okay, and so in this case what we're doing is we're looking for one that's a little on the basic side, because it looks like our equivalence is expected to be around 8.5. You also want to achieve the lightest color possible, because the lighter the color, the closer you're going to be to that actual change. So if you get it really, really pink, then you've already gone past that and you're already well into the basic side. There are a lot of dyes you can use, and so a lot of times you will see it like HIN standing for indicator, and that indicator turns into an anion with the H3O plus. And so you can actually use a mixture of these indicators if you're trying to see different things about the reaction that's going on, or if you don't know exactly where that equivalence point is going to be. So like phenolphthalein is a very common indicator. We use that a lot in our labs, and it's nice because if you're using it for a strong acid, strong base, it will change immediately going from the 7 to the 9, and that's the difference between like one drop. So it's a really good indicator for that, plus it's pretty cheap and easy to use. Methyl red will give you more of a transition. It'll go from the acid side from 5 to 7 and go from a pink to an almost mauve color to yellow. So it just depends on what you're trying to see and which way you're going in a titration. This is just a table of all the different types and what their ranges are, and some of them have 2 different ranges, which are good if you've got a polyprotic acid or something like that. Like I said, phenolphthalein, which is one that we use a lot, is here. It's on the high side of 7, but I mean it does. And some of these, even though they're good right in here, the transition is not as sharp as when you're going from colorless to pink, like in phenolphthalein. So that's why we use that a lot. And that's all we have for part 4.